Good afternoon. Today's topic is Gauss Law. In this video lecture, we will see the statement of Gauss Law and we will try to understand how Gauss Law can be implemented or it can be applied for determining the electrostatic fields. In the last video lecture, we have gone through determination of electrostatic fields due to point charges and also continuous charge distributions. And in this video lecture, I hope that by the end of this video lecture, you will be able to write the statement of Gauss Law and also explain the Gauss Law and its applications for determination of electrostatic fields. Now, moving ahead, we have seen in the last video lectures that the electric field intensity of a charge, let us suppose a charge is present here, and I want to measure the field at this particular point P, which is at a distance of r. So the electric field of the charge Q at this point P is given by the equation Q by 4 pi epsilon naught epsilon r into r square. So this is constant. This is the charge itself. R is the distance between these two. And UR indicates a unit vector which is along the line joining the 2 points. So this is the expression for electric field due to a point charge. Now, we will move on to a little bit more modified version of this one. Now let us suppose if I do consider a point, a charge and a point. Now let us suppose I assume that these two are lying in a particular plane, in a two-dimensional plane. Now let us suppose if this is a two-dimensional plane where my charge and my point of consideration are lying. Now I'll consider a unit vector which is normal to this plane. So if I consider a vector which is normal to this plane, then it will be in this direction, vertical direction, right? So now let a unit vector normal to the plane of the surface element is given by n bar. So normal component of the electric fields. So E is assumed to be the normal, is assumed to be the electric field. So the normal component of this E vector is given by E bar dot n bar. Right? Now, so surface integral of this normal component of field. Okay, so I am going to take the entire component of or the entire surface. Now, surface integral of this normal component of the field. So I know this automatically the value of this one. This is Q by 4 pi epsilon naught epsilon r square into UR. This is up to this is E bar, right? So this is the expression. This is the surface integral of this electric field, normal component of electric field over the entire surface area ds. Now this is my surface area. I am considering now only this particular surface area, and now I will be integrating it over this entire surface area. Okay. So which means that my plane earlier, it is a plane which consists of my point of consideration and also my charge. Now I am going to take a normal vector which is perpendicular to these two. It will be in this format. Okay. Now, having said this, if you see, there is a dot product of two vectors here, which is nothing but UR unit vector along R. This is unit vector along R, and the normal component of this unit vector along R. See, so my unit vector will be in this plane itself, whereas n bar will be in this direction. So the normal component of UR dot n bar, it is nothing but the projection of ds on a plane perpendicular to the vector, isn't it? So this is a vector which is lying on the plane. So this is the projection of this vector. Now the projected area divided by r square is called as a solid angle, subtended by that ds, which is defined by d omega. So what is this d omega? What is the solid angle? Normally you might have seen in a circle that every arc basically, this is the point O. Now this arc will be subtending an angle, right? This is called as a theta. This is a two-dimensional representation. Now let us suppose if it is a three-dimensional, you don't call it as a circle, you will call it as a sphere, right? Now let us suppose a sphere is also just like a circle, but it is a three-dimensional one, and it will be having a radius. Now assume that there is a sphere of unit radius centered at O. See, this is a sphere. Assume that this is a three-dimensional one. So a three-dimensional one, if you see, yeah, a three-dimensional. Now the area of the sphere, which is cut out by a conical surface. Now let us suppose this is a conical surface, right? Now if I take it for a circle, I will call it as an arc, right? Now whereas for a sphere, which is a three-dimensional one, I'll take it as a cone, right? So now this area, which is being cut out by this conical surface with the center at O, and having the perimeter of the surface A, this is the perimeter of the surface A for its base. Okay, this is my entire right surface area. So this is at the one. So the angle which is subtended by this one is called as an omega. Okay, so how omega is being given? Omega is equal to A by R square, where A is the surface area and R is nothing but the radius of the sphere. So this is termed as solid angle. Now we will employ this solid angle to my to our point. Now here also, now let us suppose if I am going to consider a surface area ds. Now let us suppose this is a surface area ds. Okay. Now, each point on the boundary of which is jointed to O by a straight line. Now let us suppose this is my ds now. Okay. So now this is entire, this is a sphere, okay. I am considering only a part of the outer perimeter of the sphere and I am joining it to the center of the sphere, okay. Now see, this angle which is made by this one is called as solid angle, okay. So if you carefully see, just as we have done in the previous case, this is a cone, right? Cone. Now I am going to construct a sphere S dash with O as a center and radius R. So whatever the solid angle which is subtended by ds is equal to that subtended by ds dash, which is an element of the spherical surface S dash centered at O. So for a closed surface, now this is a closed surface, ur dot n by r square into ds. Okay. So I am going to do this for an entire surface now. So in other words, to simply say, let us suppose if this is a plane. Now I want to consider a point P here. Now what is the projection of this entire plane onto this point P can be taken as just like a solid angle if there is a sphere. Now this entire, this area, whatever area, what angle it is tending, it is subtending at that particular point. I'll call it as a solid angle and I'll extend it to a sphere. So if it is a closed surface, so the previous expression now, it becomes like this, ur dot n by r square into ds. So instead of ds, what I will take? I'll take it as s dash. Now this is my actual area, but I'm considering it to be similar to that of a sphere. So I'm extending it to be s dash r dash s square to ds dash. Now if you carefully see this particular one, it is nothing but unit vector, which is this is unit vector which is normal to the surface. So if any unit vector which is normal to the surface means you are considering the entire normal surface area of the sphere. So what is that equal to? It is equal to surface area of a sphere. You know that it is equal to 4 pi r dash square, if r dash is the radius of the sphere, right? So 4 pi r dash square by r dash square, it is equal to 4 pi. So this is your closed surface. Now earlier in this case, what we have done? So we have tried to compute this one. Now this we have tried to replace E bar with its original equation. Now in this one, all these are considering as constant. Okay. Now surface integral is pushed back here. Now what this one is? This one we have tried it Instead of considering this as a planar space, I am considering it as a sphere. So this value has become into 4 pi, right? So this is my expression. So 4 pi will get cancelled. Now this is my remaining expression. Okay. If I push this one to here, so this is the expression. And you know, we have already done this in the previous SLT 5 also. This is permittivity into electric field. It gives electric flux density. Okay. So because we know that D is equal to epsilon into E bar. So I have replaced this one. So this is called as a Gauss law. Okay. The surface integral of the electric flux density vector normal to its surface is equal to the charge enclosed by the surface itself. So that is what is Gauss law. Okay, the surface integral of the normal component of the electric flux density vector is equal to the charge enclosed by the surface. This law was first formulated by Lagrange and later it was followed by Carl Friedrich Gauss in the year 1835. So very long back, nearly 200 years we are getting it. So it seems, let us suppose there is a straight line. This is a line of charge, let us suppose. Now, if I consider that there is a cylinder type of, okay, so let us suppose this is a line charge. Now, this line charge is having some line charge density. Then automatically what happens? It will develop a field around it, right? So the field will be just like a cylinder around it, isn't it? So now, whatever the charge which is present inside this line charge, it can be computed by this particular vector. So whatever the electric flux which is coming out of this cylinder type body, I should count it and I should compute it, d bar, over the entire surface integral which is covering this entire infinite charge or finite charge. So the number of flux per unit area which is covering this charge, it is nothing but the charge which is enclosed by that surface. So this is the application of Gauss law. If I am unable to determine what is the charge of this line conductor, you better calculate how many electric lines of force are coming out, divide it with area over the entire surface, and that gives the charge. Okay. So I hope now you are able to understand the Gauss law and its applications for determination of electric field. Thank you. In the next video lecture, we will see how to apply Gauss law for determination of electrostatic fields. Thank you.